In this section, we're going to continue our discussion on probability and look at a few additional examples. So first, just to review, the definition for probability that we learned in the last section is that probability is the chance of something happening. And we have our formula for probability, the number of favorable outcomes divided by the number of possible outcomes. So we're going to begin with an example where we toss a coin twice. Now the first thing that we want to do, because we know that probability is based on a sample space, is we want to list out the sample space for this particular example. Now we talked about this in the last presentation, so we're just very quickly going to review this. Remember, your sample space is a list of all possible outcomes. So when you toss a coin twice, one possibility is that you get heads the first time and heads the second time. Another possibility is that you get tails the first time and tails the second time. A third possibility is that you get heads on the first toss and tails on the second toss. And finally, your last possibility is that you get tails on the first toss and heads on the second toss. And as you recall, we made a point of saying that these two outcomes were considered different, even though they were both one head and one tail, because they're considered different because of the order. All right, so now that we know the sample space, let's look at a couple of probability problems. All right, so I've transferred our sample space over to this new slide. And our question asks us first to find the probability of getting exactly one tail when flipping a coin twice. Okay, so we want to look at our sample space and we want to determine how many of these outcomes are favorable. How many of these outcomes have exactly one tail? So this is an outcome that has exactly one tail, and this is an outcome that has exactly one tail. This outcome has two tails, so it wouldn't count. And this outcome has 0 tails, so it wouldn't count. We just want the ones that have 1. So I know that the top number for my probability, the number of favorable outcomes, is 2. The number of possible outcomes, which goes on the bottom, is the number of outcomes in the sample space. So we simply need to come to our sample space and count the number of outcomes. So 1, 2, 3, 4, and we'll put 4 on the bottom. Now remember that you always want to reduce your fractions. So 2 out of 4, 2 over 4, is the same thing as 1/2. Our second problem says find the probability of getting exactly 2 tails when flipping a coin twice. So again, we look at our sample space and we determine how many outcomes are favorable. How many outcomes have exactly 2 tails? And there's only one outcome that has exactly 2 tails. And so 1 is going to be the number of outcomes that are favorable. And how many outcomes are possible? Again, the number of possible outcomes is the number of outcomes in your sample space. So we count 1, 2, 3, 4, and the 4 goes on the bottom. And so the probability of getting exactly 2 tails when we flip a coin twice is 1 out of 4. Now, what if we change the problem and we say that we want to toss the coin 3 times? Okay, what is the sample space for that? Now again, we did this in the last presentation, so I'm just very quickly going to review it here, but if you feel like you need more detail, you would want to go back and look at the presentation from the last section where we went over this in quite a bit more detail. So if I'm going to flip a coin 3 times, it is recommended that I make a tree diagram to list out my outcomes. And so remember that your tree diagram is going to have 3 columns because you're tossing the coin 3 times. So we're going to have a column for the first toss. We're going to have a column for the second toss. And a column for the third toss. And then remember that you're going to place a point to the left, which is your starting point. And then you say to yourself, when I toss the coin the first time, that coin might end up showing heads, or it might end up showing tails. If the coin were to toss heads the first time, and I pick it up again and toss it again, I could get another head, or I could get a tail. If the coin were to toss tail on the first toss, and I pick it up and toss again, I could get a head, or I could get a tail. And then as we move to the third toss, we do the same thing. So we say to ourselves, if I toss heads on the first toss, heads on the second toss, and then I pick up the coin again, the coin could land heads for the third time, or it could land tails. And we talked about once you see that pattern of what's happening, going ahead and completing the tree diagram. So we will branch off for each of these with heads and tails. And then we use that tree diagram to list out our sample space. So one option, the first option, would be this: head, head, and head. The next option would be head, head, and tail. And then we continue walking through this, writing down the 8 different options. So then we would have head, tail, head, head, tail, tail. Then we move to the second part of the tree diagram down here. We have tail, head, head, tail, head, tail, 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 head, tail, tail, tail. Okay, keep in mind that you need to be able to list out the sample space if you're going to work a probability problem where you're tossing 3 coins. So you want to practice this so that you're able to list out these possible outcomes. All right, so now that we have our sample space, let's go ahead and look at our probability problems. So again, I've transferred the sample space to the new screen just so that we can see it a little bit easier. And our first problem says, find the probability of getting exactly 1 head when flipping a coin 3 times. Okay, so for the number of favorable outcomes, I want to look at the ones that have exactly 1 head. All right, so that is going to be this one. This one has 1 head. This one has 1 head. And that one has 1 head. And so we have 3 outcomes that are favorable. How many outcomes are possible? Remember that to do the possible number of outcomes, you are simply going to count the number of outcomes in your sample space. So we go through and we count 1, 2, 3, 4, 5, 6, 7, 8, and 8 goes on the bottom. All right, for our next problem, it says find the probability of getting exactly 2 heads when flipping a coin 3 times. So again, how many are favorable? How many have 2 heads? This one has 2 heads. This one has 2 heads. This one has 2 heads. And that's all of them. Okay, and so we have, again, 3 that are favorable. The number of possible outcomes would be the number of things in the sample space. So again, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's move on to a different type example. What if we rolled 2 dice? We talked about this on the last presentation. We talked about what that sample space is going to look like. And more specifically, we talked about the fact that in that sample space, that there are 36 possible outcomes. All right, we also discussed the fact that if you look at a particular outcome, like 3-1, that you should also expect the reverse to be there as well. So if 3-1 is an outcome, 1-3 is also an outcome. And that holds for every combination that we have in the sample space except for the ones where we have doubles. So a 3, 3 is just a 3, 3 and it's not listed twice. Okay, so keeping that in mind, let's go ahead and look at a problem with dice. So suppose you roll 2 dice, find each of the following probabilities. Find the probability that the sum is greater than 9. So first of all, I have to think about what that's asking me for when it says the sum is greater than 9. Numbers greater than 9 would be a sum of 10, 11, and 12. Remember that 12 would be the highest sum you can roll with the 2 dice. So let's go through and make a list of the ways that we can roll these numbers. So with 2 dice, to roll a sum of 10, I could roll a 5 and a 5. I could roll a 6 and a 4. And I'm going to flip that around and make a 4 and a 6 as well. Okay, and then I think that that's it with the 2 dice for the 10. All right, what about for the 11? For the 11, I could roll a 5 and a 6 and a 6 and a 5. And that's it for ways to make 11. And for a 12, the only way to roll a 12 is to roll a 6 on both die. All right, so how many outcomes do we have that are favorable? So let's count. 1, 2, 3, 4, 5, 6. So we have 6 outcomes that are favorable out of what? All right, so remember that we said that for our sample space, we had 36 possible outcomes. So that 36 is going to go on the bottom. And then we would want to reduce that fraction. Reducing it on your calculator is probably going to be easiest, but if you don't have a calculator that does that, then you would want to say to yourself, both the 6 and the 36 are divisible by 6. 6 divided by 6 is 1. 36 divided by 6 is 6. All right, so we have a 1 in 6 chance of rolling a sum that's greater than 9. For our next problem, we have a sum of 4, 8, or 12. So we're going to do the same kind of thing. We're going to look at how can we roll a 4, how can we roll an 8, how can we roll a 12. So for a 4, we could roll a 1 and a 3, and a 3 and a 1, and a 2 and a 2. For an 8, we could do, let's see, we could do a 2 and a 6. We could do a 3 and a 5. We could do a 4 and a 4. And for a 12, we said the only way to do it was double 6s. So again, how many are favorable? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 ways to do it. How many are possible? Again, remember 36 possible outcomes. And then we look at reducing that fraction. So both the 9 and the 36 are divisible by 9. So 9 divided by 9 is 1. 36 divided by 9 is 4. And so we have a 1 in 4 probability of rolling a sum of 4, 8, or 12. All right, continuing with this example, we're still looking at our 2 dice. Find each of the following probabilities. These are a little more difficult. We want to first find a probability that we get an odd number exactly once on the die. Okay, so I'm going to have to go through and kind of make a list of things that will meet this criteria. We need one odd number on the die, but only one. So I'm going to try to do it systematically. So I could do a 1 and a 2. I could do a 1 and a 4. I can do a 1 and a 6. So those would be the only things that start with a 1, where we only have one odd number, right? Because if like it was 1 and 3, that would be 2 odd numbers. All right, so for the 2, I could do 2 and 1. I could do 2 and 3. I could do 2 and 5. Again, we need the ones that start with 2s that only have one odd number. All right, for the 3s, I can do 3 and not 1 because that would be 2 odd numbers. So 3 and 2, 3 and 4, 3 and 6. For the 4s, we could do 4 and 1, 4 and 3, 4 and 5. For the 5s, 5 and 2, 5 and 4, 5 and 6. And then finally for the 6s, 6 and 1, 6 and 3, 6 and 5. Okay, so it may take you a minute to list those out, but really that's going to be your best way to do it. And then you count. So how many do we have? So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 18 over 36 possible outcomes, and that will reduce to 1/2. So we have a 1 in 2 chance of having an odd number exactly once on the die. Okay, what about the second one where we have even numbers on both dice? So let's again try to make a list of ways that we can do even numbers on both. All right, so I know that I wouldn't have anything that starts with a 1 because that would give me an odd number. All right, so even numbers on both could be 2 and 2, 2 and 4, 2 and 6. I wouldn't have anything that begins with a 3 if my stipulation is even numbers on both. All right, I could have some 4s, so I could have 4 and 2, 4 and 6, 4 and 8. I wouldn't have any that start with a 5, but I could have 6 and 2, 6 and 4, 6 and 6. All right, so how many are favorable? 1, 2, 3, 4, 5, 6, 7, 8, 9. 36 possible. Again, when we're reducing that fraction, we've already reduced this one once, but both are divisible by 9. And so we would end up with 1 over 4. All right, so the last example that we're going to look at says, what if we have a random set of 3 kittens? What is the sample space? And we're asking about the gender of these 3 kittens. Now, again, we've done this example. We didn't do it with cats, but we did it with children. So if you need a lot of detail for setting up the tree diagram, you could look back at the last presentation where we talked about the genders of the 3 children. All right, but it doesn't matter. 3 cats, 3 dogs, 3 children, 3 coins, it's all going to work the same way. Okay, so I'm going to do 3 columns. I'm going to do cat number 1, cat number 2, cat number 3, and place a starting point. I know the first cat can be male or female. If the first cat is male, the second cat could also be male or could be female. So I'm going to branch off for both of those. And then again, if the first cat is male and the second cat is male, then the third cat could also be male, or the third cat could be female. And once you see that pattern of what's happening, you can go ahead and fill in, branching off of each of these with a male or female possibility. And then we would want to list out those outcomes for our sample space. So our first one would be all 3 males. And then our next one would be male, male, and then coming down for female. And then we would have male, female, male, and male, female, female. And that would take care of the top 4 there. And then as we move down, we would have female, male, male as our next one. Then we would have female, male, female, 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 male, and then all 3 females. All right, so again, keep in mind that it is going to be nearly impossible for you to answer probability problems like this if you can't list out the sample space. So you need to practice this tree diagram so that you can very quickly sketch this out and get a sample space. So again, 3 kittens, 3 dogs, 3 children, 3 coins, anything like that is going to have a very similar sample space. So just get some practice in so that you can set these up and list your sample space out quickly. Okay, so again, I've pulled it over to the next slide. Let's look at a couple of probability problems. The first one says, find the probability of getting exactly 2 male kittens. So for number of favorable, I need the ones that have 2 males. That would be 1. That one has 2 males. That one has 2 males. Okay, and that's it. So my number of favorable would be 3. My number of possible, if you count the number of things in the sample space, you'll get 8. All right, so our next problem says find the probability that the set contains more females, and it should say more females than males. So let me make that correction real quick here. So I think I just ran off the screen here. More females than males. Okay, so let's go through and circle the ones that have more girls than boys. So this one has more females than males. That one has more females than males. That one has more females than males, and that one has more females than males. So we have 4 that are favorable. Again, possible is the number in the sample space, so you count everything, and we would see that we have 8. And 4 out of 8 is going to reduce to 1/2. So we have a 1/2 chance or 1/2 probability that the set contains more females than males.